Dear students, using weighted residual approach, so how to develop an expression for the fluid flow for a Newtonian viscous fluid on an inclined flat surface. Let us discuss in this video. So this is the problem I have considered. The governing equation for a fully developed steady laminar flow of a Newtonian viscous fluid on an inclined flat surface is given by mu d square v by dx square plus rho g cos theta is equal to 0. This expression is applicable between the limit 0 to L. Okay. So where mu is nothing but the coefficient of viscosity, v is the velocity of flow, rho is density of the flowing fluid, g is acceleration due to gravity, and theta is the inclination between the inclined plane and the vertical plane. Okay. So the boundary conditions of the problem can be directly observed to be boundary conditions. Actually, these conditions will be directly given in the problem. dv by dx at x is equal to 0 is equal to 0. That is, at the initial position, that is at x equal to 0, there will be no change in the velocity. Okay, there will be no velocity gradient. So the change in velocity with respect to x will be 0. That will be considered as one of the boundary conditions. And by observing the velocity profile, so from the initial position, if we consider the velocity at x is equal to L will be 0. Okay, so here velocity will be 0, here velocity will be maximum. Okay. So the second boundary condition can be considered to be velocity at L is equal to 0. Okay. So the second condition is known to be no slip condition, and the first condition is generally known to be no shear stress condition. Okay. So how to solve this problem to develop the expression for the velocity of the flowing fluid for the considered problem using weighted residual approach? So the step-by-step procedure we will be discussing in this lecture video. So for solving these kind of problem using weighted residual approach, initially we have to select a trial function which should satisfy the given boundary conditions. Okay. So in the step 1, let us consider a trial function. So usually polynomial type of functions are considered as trial functions. So here since the order of the governing differential equation is 2, we can consider the trial function for the velocity with 3 terms, a1x plus a2x square. So the order of the trial function should be chosen for the order of the governing differential equation. Okay. So we can keep this equation as equation 1, that is the governing differential equation for the given problem, and the standard polynomial function considered as the trial function for the given problem can be taken as equation 2. Okay. So we have to modify these general equation to be well suited for the given problem by substituting the given boundary conditions into this. Okay. So for applying the first boundary condition, we have to have the equation 2 in its differential form. So first, because the first condition is of differential form, okay, dv by dx, but in equation 2 we are having the expression for v of x. So by differentiating once equation 2 with respect to x, we can directly apply the first boundary condition. So differentiate equation 2 once with respect to x. So dv by dx will be The differential form for a0 is 0 plus a1 into x is 1 plus a2 into 2x. So now we can apply the first boundary condition in equation 3. That is, at x is equal to 0, dv by dx is equal to 0. Okay, so equation 3 becomes a1 plus a2 into 2 into 0. Okay, so when x is equal to 0, du by dx equal to 0, so we will be arriving at a1 is equal to 0. Okay, so next we can apply the second boundary condition, v of L is equal to 0. That is, at x equal to L, velocity v equal to 0. So that condition can be applied in equation 2 directly. Okay, so in equation 2, when we are applying the value of x as L, the velocity function will be 0. Okay, so apply the second boundary condition in equation 2. So v of L is equal to a0 value is there, which is not equal to 0, plus a1x. So we have already found out in the previous step as a1 is equal to 0, plus a2x square. So a2 into x instead of x, we have to substitute L. Okay, so is equal to 0. This is the condition. When x equal to 0, v of L is equal, when x equal to L, velocity function as 0. So a0 is equal to minus a2 L square. So by applying both the boundary condition, we have found out the values for a0 and a1. So substitute the values of a0 and a1 in the general trial function equation, that is equation 2. v of x is equal to a0 as minus a2 L square plus a1 as 0x plus a2 x square. So simply by keeping a2 outside, x square minus L square. So this is the required trial function for our present problem. Okay, the next step for following the weighted residual approach is to formulate the residual function. Okay, for getting the residual function, we have to raise this trial function presented in equation 4 to the order of the given differential equation. So the given differential equation is of order 2. So we have to raise the given the considered trial function presented in equation 4 to order 2. Okay, so for that we have to differentiate equation 4 with respect to x twice. So dv by dx is a2 into differential form for x square is 2x minus L square 0. Then d square v by dx square a2 into 2, simply 2a2. Okay, so by comparing this d square v by dx square value with the d square v by dx square value presented in the governing differential equation, we can arrive at the residual expression. So by replacing the d square v by dx square term in the differential equation by the d square v by dx square value, we have found out and presented in equation 5, mu into d square v by dx square value we have found as 2a2 plus rho g cos theta. So this is called as the residual function, residual R. Okay, so one of the weighted residual approaches is known to be point collocation method, a very simple approach. Point collocation method, or it is otherwise known to be simply collocation method. So in this method, by equating the found out residual value directly to 0, we can obtain the required result. Okay, so this is the concept. So the residual value we have found out and keep in equation 6. So mu into 2a2 plus rho g cos theta is equal to 0. So mu into 2a2 is equal to minus rho g cos theta. That gives a2 is equal to minus rho g cos theta divided by 2 mu. Okay. So now we can apply, substitute the value of a2 in the found out trial function presented in equation 4. P of x is equal to a2 into x square minus l square. So minus rho g cos theta divided by 2 mu into x square minus l square, or simply we can write like this: rho g cos theta divided by 2 mu into L square minus x square. So this is the required expression.